Let us then recall what is the Laplace transform f of s of a real-valued function f of t, where t, too, is a real variable. This Laplace transform is complex valued, and s, the variable on which it depends, is also complex. This Laplace transform f of s, also denoted by L of f of t, is given by an integral. So it is an integral transformation. Here we have f of t, and this exponential here is the kernel. The Fourier transform f of j omega is the restriction of the Laplace transform to complex values of s which are purely imaginary, and thus given by j omega, where omega is the coordinate along the imaginary axis. Here we have a point given by j omega with positive omega. Here we have another point also given by j omega, but this time omega is negative. Of course, here we have 0. It is also j omega with omega equal to 0. So here I may denote the Fourier transform by f of t. The integral is the same, save that in the kernel I replace s by j omega. Now, these definitions of the Laplace and the Fourier transforms are called unilateral. They are the most usual definitions of the Laplace and Fourier transforms, and they are the ones we have used until now, for a very simple reason. Until now, we have always applied the Laplace and Fourier transforms to signals in time that begin at t equal to 0. Our function in time need not even exist for values of t which are negative. Or we may simply presume that our function is equal to 0 until the signal begins at t equal to 0. That is the advantage of using the unilateral Laplace transform or the unilateral Fourier transform for the signals which we have used until now. But remember, in this class, we are going to study the cross-spectral density. And the cross-spectral density of two signals, x and y, is the Fourier transform of the cross-correlation of x and y. I write it here depending only on omega, though, as I said, it depends on j omega, but it is usual in this case to omit the imaginary unit j. Now, remember that this cross-correlation of two signals is not, in the general case, an even function, symmetric around the vertical line at tau equal to 0. It can be anything like this, for instance. So, it exists for both positive values of tau and negative values of tau, and is not an even function. Consequently, it is not reasonable to use a unilateral transform with this. That is why, when calculating the cross-spectral density and the power spectral density, we use bilateral definitions for both the Laplace and the Fourier transforms. They are just like their unilateral counterparts, but the integral is calculated from -infinity to infinity, and thus we sweep the entire real axis and take into account the evolution of the function not only for positive values, but also for negative values. Just one final comment. One might say, all right, the cross-spectral density is the Fourier transform or the Laplace transform. As I said, sometimes it is given as the Laplace rather than the Fourier transform of the cross-correlation, which is not an even function. Consequently, we must take into account separately both tau larger than 0, tau less than 0, and these are not the same. But when we are calculating the power spectral density, we will have the Fourier or the Laplace transform of the autocorrelation of a signal. And remember, the autocorrelation of a signal exists, right, for both positive and negative values of tau, but is necessarily symmetrical with respect to this vertical axis here. It is an even function. That is why we normally even plot it only for positive values of tau. It would be a waste of space to do that. Can't we here use the unilateral Fourier transform? Or if we give it as a Laplace transform, as the unilateral Laplace transform of the autocorrelation of x. Yes, but remember that the autocorrelation of a signal is the cross-correlation of the signal with itself. And in the general case, the cross-correlation is not even. And that is why, whether we use the Fourier or the Laplace transform to give the cross-spectral density, we always use the bilateral transform. And thus, since this is the general case and this is a particular case, and since in the general case we use the bilateral Laplace transform, we here use the bilateral transform as well. Notice that it is sometimes difficult to see whether we are using the unilateral or the bilateral Laplace transform. We always use L and F for both. But when you see a power spectral density of a signal or a cross-spectral density of two signals, you can be sure that we are using the bilateral transforms, not the unilateral ones.